Okay, so we just tested on electron configurations and quantum numbers. In that chapter, one of the last things we did is we identified our highest occupied energy level, and that's also known as the valence shell. And we determined how many valence electrons were in the atoms. And the reason we're focused on the valence electrons is because those are the electrons that take part in bonding, that participate in bonding. So today's lesson is on chemical bonding. It's an introduction to chemical bonding. And the information comes from Chapter 7 and Chapter 8 in our book. One thing we want to revisit is the concept of electronegativity. Electronegativity we learned about in Chapter 5-6 when we talked about the periodic trend. The symbol for electronegativity is a Greek letter, we call it a chi. And the definition of electronegativity is the ability of an atom to attract or pull the electrons towards itself when it's bonded to another atom. It's kind of like a tug of war between the atoms. In class, I will give each of you an electronegativity table. It will look like this, and it will have the actual values for all the electronegativities of the atoms on the periodic table. Remember, we learned in Chapter 5-6 that the trend for electronegativities, as we go up and across the periodic table, the electronegativities we learned tend to increase. And you see that happening here. Francium is a 0.7, and as you go up the alkali metal family, notice it is increasing, and then as you go across towards fluorine, you see fluorine is the most electronegative element on the table at a 4.0. Also notice the noble gases are not shown here because remember, they have zero electronegativity. They're already stable. We're going to focus mainly on ionic bonding and molecular or covalent bonding in this chapter. But first I want to compare and contrast ionic and molecular compounds, which we studied how to name and write these formulas back in Chapter 9. Recall that an ionic compound consists of a metal and a nonmetal, whereas a molecular compound consists of two nonmetals. They bond differently, and we will see that as we study our chemical bonds. The ionic bonds are stronger than the covalent bonds. They have very high melting points and high boiling points. Also, ionic compounds are much harder. If you were to try to crush them, they'll be harder. It's a stronger bond. In the molten state, that means if you melt it, or if you were to put it in water and dissolve it, where it would be aqueous, ionic compounds conduct electricity. And so we call those kind of compounds electrolytes. We have electrolytes in our bodies, and they're essential for us to have proper brain function and muscle function. For your heart to work correctly, you need to have the proper amount of electrolytes in our bodies biochemically. Ionic compounds consist of positive and negative ions. That's the word ionic implies there's ions there. And remember, we have cations and anions. And they're bound together by in a crystalline solid. Think about the most common ionic compound is table salt, NaCl, sodium chloride. It's a white crystalline solid at room temperature, and if you dissolve it in water, it will conduct electricity. Now, the molecular compounds, when they dissolve in water, they do not conduct electricity. They're called non-electrolytes. The reason is because the water doesn't actually pull the ions, doesn't actually pull the atoms apart. So there's no ions moving around in solution in order to conduct. The molecular compounds remain intact, and they consist of molecules. They move around independently. So like when you put, for example, sugar in water, the water does not pull the sugar apart into its carbon, hydrogen, and oxygen atoms. So since there's no ions present, there's no conductivity there. And I will show y'all an animation in class of this. So I said we were going to learn about chemical bonds. What a chemical bond is the force or the energy that holds atoms together. There are three types of bonding that we're going to be studying in this unit. One thing I want you to remember always is that all of the elements want a noble gas electron configuration. So what does that mean? It means they want to have a full valence shell. They want to have 8 valence electrons, or in the case of those that want to look like helium, they want 2 valence electrons. The first type of bond is an ionic bond. I'm going to be relating these to the electronegativity table that I talked about earlier and the electronegativity values. One thing we're going to notice about our ionic bonds is that when we find the electronegativity difference, that's what this delta X means. The delta, the triangle, means difference, means you subtract, and the X is the electronegativity symbol chi. When we subtract our electronegativities at the end of this lesson, we will see that if it's an ionic bond, it will have an electronegativity difference of 1.7 or greater. Again, if it's ionic, you have to have a metal ion and a nonmetal ion. And what happens with your ionic bond is the valence electrons are transferred. That's a very important thing to remember. They get transferred from the metal to the nonmetal. So let's take, for example, think about sodium. We learned that sodium has an electron configuration of 1s2, 2s2, 2p6, and here we're getting to the valence shell. He ends in a 3s1. And then think about chlorine, Cl. Chlorine's electron configuration would be 1s2, 2s2, 2p6, 3s2, and then 3p5. All right, so in the highest occupied energy level, here we have the third for sodium, and we have the third for chlorine. This is where the valence electrons are located. And so what's going to happen here, see, sodium needs to lose this valence electron. So what he's going to do is he's going to actually transfer it to the chlorine. Notice if he were to give this one electron to the chlorine, that would give chlorine 6 in the p orbital. So if he transfers that one electron, that makes this leaves behind 1s2, 2s2, 2p6. Notice that's a full valence shell. He would have 8 valence electrons. And what happens is sodium becomes the sodium ion now because he gave away his valence electron. When he gives it to chlorine, that gives chlorine the 6th electron here in his p orbital. 6 plus 2 gives you 8 valence electrons now, and that makes chlorine become the chloride ion. So what happens is the opposite charges here that are created when the ions form pull the ions together, the oppositely charged particles together, and it's the opposite charges that attract. This is our strongest bond, remember. Now, the covalent bonds are the types of bonds that are found in our molecular compounds. There's 2 types of covalent bonds. There's nonpolar covalent, and then we'll look at polar covalent on the next slide. Nonpolar covalent bonds share their electrons, but they share them equally, 50-50. You have 2 nonmetals, and basically what you have here is 2 elements with very similar electronegativities. The word co means the prefix co means they cooperate, and valent refers to their valence electrons. So they're sharing their valence electrons. We're going to find with this type of bond, when we do our electronegativity difference, it will end up equaling between 0 and 0.4. That will be our range. Usually, these occur between the same atoms, like with our halogen hungs.